The discovery of the interstellar comet 3I or Atlas has captured the imagination of scientists and the general public alike, offering a rare glimpse into material that originated far beyond the boundaries of our solar system. Newly released telescope images reveal that this mysterious object is ejecting a massive jet of gas and dust toward the Sun, a behavior that, while visually dramatic, is entirely consistent with what astronomers expect from an active comet. Observed in late June and officially confirmed by NASA in early July, 3I or Atlas represents only the third known interstellar object ever detected passing through our cosmic neighborhood. Its appearance provides researchers with an extraordinary opportunity to study matter formed around another star, potentially billions of years before our own Sun even existed. What makes 3I or Atlas particularly fascinating is not just its interstellar origin, but also its impressive size and apparent age. Scientists estimate that the comet measures between 3 and 7 miles in diameter, making it significantly larger than the previous two known interstellar visitors, Oumuamua and 2I Borisov. This considerable size suggests that it may have survived for immense periods of time, traveling through interstellar space for billions of years before finally drifting into our solar system. During this journey, it would have been exposed to intense cosmic radiation, extreme cold, and gravitational influences from passing stars, yet it remained intact enough to display classic cometary behavior upon encountering the Sun's warmth. The latest images of 3I or Atlas were captured on August 2nd using the 2-meter twin telescope at the TED Observatory in Spain's Canary Islands. Astronomers combined 159 individual exposures, each lasting 50 seconds, to create a detailed composite image of the comet. In this image, the nucleus appears as a dark central dot surrounded by a luminous cloud of gas and dust known as the coma. Within this glowing halo, researchers observed a striking fan-shaped disruption, indicating the presence of a powerful jet of material blasting outward. Marked in purple in analysis images, this jet is oriented toward the Sun, giving the impression that the comet is firing a stream of matter directly at our star. Although this visual might seem unusual or even suspicious to non-scientists, experts emphasize that it represents normal cometary activity. According to Miguel Serraricat, an astrophysicist and chief science officer at the TED Observatory's Light Bridges Research Institution, such sunward-pointing jets are a well-known feature of active comets. In communications with Live Science, he explained that while a comet's main tail typically stretches away from the Sun, jets can form on the Sun-facing side and shoot material in the opposite direction. This apparent contradiction arises from the physical processes that govern how comets respond to solar heat. Comets are often described as doughty snowballs, composed of ice, frozen gases, dust, and rocky material. When a comet approaches the Sun, solar radiation heats its surface, causing volatile substances such as water ice, carbon dioxide, and carbon monoxide to sublimate, that is, transition directly from solid to gas. This process releases trapped dust and particles, forming the characteristic glowing coma and tail. However, this heating does not occur evenly across the comet's surface. Variations in composition, texture, and structural strength mean that some regions heat up and release gas more rapidly than others. When a particularly weak or volatile-rich area warms sufficiently, pressure can build beneath the surface. Eventually, this pressure is released in the form of a jet, similar to a geyser erupting through ice. These jets can eject material at high speeds, sometimes propelling dust and gas thousands of miles into space. If such an active region lies on the Sun-facing side of the comet, the resulting jet will naturally point toward the Sun. Meanwhile, the overall tail continues to be shaped by solar radiation and the solar wind, streaming away from the star. In the case of 3I or Atlas, the observed jet aligns perfectly with this established understanding of comet behavior. The images strongly support the conclusion that the object is a natural, icy body responding to solar heating in a predictable manner. This evidence is particularly important because a small group of researchers has controversially suggested that the object could be an artificial probe or alien spacecraft. These claims, largely based on the comet's unusual origin and trajectory, have attracted significant media attention, but remain unsupported by solid scientific evidence. Most astronomers reject the alien hypothesis, emphasizing that extraordinary claims require extraordinary evidence. The physical characteristics of 3I Atlas, including its coma, tail, and now clearly visible jet, are consistent with known cometary processes. Nothing in the data so far suggests artificial construction, propulsion, or control. Instead, the object behaves exactly as a comet composed of ice and dust would be expected to behave when exposed to intense solar radiation for the first time in billions of years. The interstellar nature of 3I, our Atlas, however, does make it scientifically priceless. Unlike comets formed within our solar system, which share a common origin in the early solar nebula, interstellar comets originate around other stars. Studying their composition can therefore reveal information about planetary formation processes elsewhere in the galaxy. By analyzing the light emitted and absorbed by the coma and jets, scientists can determine which molecules are present and compare them with those found in local comets. Similarities may indicate that planet formation follows universal patterns, while differences could suggest diverse chemical environments across star systems. Another intriguing aspect of 3I, our Atlas, is its apparent age. If it truly dates back billions of years before the Sun formed, it represents a relic from an ancient era of the Milky Way. Such objects could contain preserved material from early generations of stars and planetary systems. In this sense, the comet functions like a cosmic time capsule, offering insight into the conditions that existed long before Earth and its neighboring planets came into being. The journey of 3I, our Atlas, into our solar system was likely the result of gravitational interactions in its home system. Many comets are ejected from their birth environments by encounters with giant planets or nearby stars. Once cast into interstellar space, they drift for eons, following unpredictable paths influenced by gravity. Eventually, a tiny fraction of these wanderers pass close enough to another star to be captured temporarily or to swing through its planetary system. Our detection of 3I, our Atlas, is therefore a rare stroke of astronomical luck. Technological advancements have played a crucial role in making such discoveries possible. Modern sky surveys continuously scan large portions of the heavens, searching for moving objects that do not match known asteroids or comets. Sophisticated software then analyzes these observations to identify unusual trajectories, including hyperbolic paths that indicate interstellar origin. Without these systems, 3I, our Atlas, might have passed unnoticed, its secrets lost to space. The publication of the composite image on the Astronomers telegram in October allowed researchers worldwide to examine the data and discuss its implications. Although the findings have not yet appeared in a peer-reviewed journal, the observational methods and interpretations are consistent with established astronomical practices. Further observations from other telescopes are expected to refine measurements of the comet's size, rotation, activity levels, and chemical makeup. As 3I, Atlas, continues its journey through the inner solar system, its activity may change. Increased heating could strengthen existing jets or create new ones, altering the shape of the coma and tail. Over time, volatile materials may be depleted, causing activity to decline. Eventually, the comet will move away from the Sun, cool down, and resume its long, silent voyage through interstellar space, perhaps never to be observed again. Beyond its immediate scientific value, the story of 3I, our Atlas, highlights humanity's growing ability to study the wider galaxy. Just a few decades ago, the idea of detecting and analyzing objects from other star systems seemed almost impossible. Today, astronomers can not only identify such visitors, but also examine their physical processes in remarkable detail. Each discovery expands our understanding of the universe and our place within it.